Hello and welcome to our project presentation. I'm Hong Yang and I'll be starting us off with an introduction to our study on lyrics generation using deep learning models. To begin, let's talk about what motivated our study. For a long time, there existed a notion that computers are incapable of true creativity, that the driver behind meaningful innovation will always require significant human input at its core. However, in recent times, with the rapid rise of large language models, it is apparent that while not necessarily in the same way as humans, AI models have grown to be able to understand and interpret semantic meanings and connections between words beyond just a superficial level, many times even understanding nuances in a sentence better than humans in practice. Hence we had the thought, why not try and see how far this goes? Typically, a song has a title which conveys its central theme, and a genre which influences the style of these lyrics. We were interested in exploring how effectively LLMs can generate lyrics when provided with just these two inputs, the song title and its genre. Our project is organized into four main stages: dataset selection and processing, model fine-tuning using prompts based on the selected datasets, lyrics generation using the trained models, and finally, evaluation and analysis of the generated results. Through this process, we aim to gain deeper insights into the creative potential of AI in the context of music. Now I'll pass the time on to Huan Bin, who will be covering the details regarding our dataset.
Hello everyone. First of all, thank you to my groupmate for introducing our project. My name is Huan Bin, and I will be sharing the dataset and model selection of our work. Our dataset comes from Congo, containing about 5 million songs with title, tag, lyrics, genre, artist, and so on, all collected from journals.com. When we looked at this data distribution, around 14.3% of songs were pop, 33% were rap, and the rest were others. So, from this, firstly, we can see that the dataset is large and diverse, providing rich text for training. And secondly, the lyrics are expressive and emotional. It's very ideal for language generation. And secondly, the structure is clear. Each record has a title and the lyrics, which makes input and output design very simple. So that's why we will choose this dataset for our project. Well, next, let's move to model selection. We fine-tuned and compared 3 small large language models. They are DeepSeek, Llama, and Queen. We decided to use these 3 models because they are open source and easy to fine-tune, and at the same time, they are lightweight and resource efficient. What's more, they come from different institutions and have distinct architectures, which makes our comparison more meaningful. While they share these common advantages, each model also brings something unique to the table. DeepSeek performs well in reasoning and text generation for both English and Chinese. Llama is widely used and known for flexible fine-tuning and high efficiency. And Queen from Alibaba is a multilingual model and excels in both languages. So by using these 3 models, we achieved a good balance between resource cost, controllability, and diversity, and our results become more comprehensive and insightful. So that's all for the dataset and model selection part. Next, I will pass the time to my groupmate, who will introduce our training methodology. Thank you for your attention.
Thanks for the last partner's introduction, and I am Ai Xiaohan, and I will continue briefly introducing the model architecture and training setup for our Q-LoRa fine-tuning experiment. The Q-LoRa stands for Quantized Low-Rank Adapter, and it combines for bit quantization with LoRa adapters to enable memory-efficient fine-tuning of large language models. As shown here, the architecture contains 3 main components. First, it represents the frozen weight model layers. These weights are not updated during training, which significantly reduces the training cost and preserves the model's original knowledge. The second module is the LoRa adapters. Insert into attention and feed-forward layers such as Q project and V project. Only these small metrics are trainable, typically less than 0.1% of the total parameters. Finally, the module indicates the 4-bit quantized computation flow. This compresses model weights using the NF4 format, reducing memory usage by roughly 70 to 75% while maintaining the near FP16 accuracy. In short, QLoRa phrases the base model as the lightweight LoRa adapters and runs all computation in 4-bit precision, making large-scale fine-tuning feasible even on limited hardware. And the next part is the training setup. We use the transformers, TIL, and PEFT frameworks for implementation. The training runs in VFlow 16 computation with 4-bit quantization. To balance efficiency and stability, we use a small batch size of 1 with gradient accumulation of 8, and gradient checkpointing is enabled to further reduce memory usage. For optimization, the training automatically applies the LMW optimizer with a cosine learning rate schedule and a 3% warm-up ratio. The learning rate is set to 2, which is typically side-tuned for LoRa fine-tuning. We use the gradient accumulation and clipping to stabilize the updates and a dropout rate of 0.05 inside LoRa adapters to prevent overfitting. After training, the LoRa adapters can be merged back into the base model for inference, resulting in a compact, efficient, fine-tuned model that performs comparably to full parameter fine-tuning but at a fraction of the cost. In summary, QLoRa provides a simple yet powerful recipe for efficient large model adaptation, combining the quantization, low-rank adaptation, and modern optimization techniques to achieve high performance on low-resource hardware.
Thank my groupmate for introducing the model architecture and generation process. My name is Wu Chenzhe, and next I'll talk about how we evaluate our models. That is, how we measure whether the generated lyrics are actually good or not. In this project, our goal is to evaluate how well each model can reproduce the original lyrics. Instead of using BLEU or log, we adopt semantic similarity based on sentence embeddings. Lyrics are highly creative and expressive, which means they often have low lexical overlap. So the generated lyrics may use very different words but still express the same meaning. However, BLEU and RUG only focus on n-gram overlap, so they fail to capture semantic consistency. Therefore, we use sentence transformers to compute cosine similarity between the generated and original lyrics. As shown in the formula, the similarity score is a cosine of two embedding vectors, and the value ranges from -1 to 1, and a higher score means stronger semantic alignment. For each model and each sample size, that is n equals to 100, 500, and 1000, we calculate 4 statistics. The first one is mean similarity, which is the average semantic similarity across all samples. It reflects overall generation quality. Minimum similarity and maximum similarity can represent the worst and best generated examples. Finally, standard deviation measures the stability of generation results. We also visualize the similarity distribution, as shown in the histogram. The x-axis is cosine similarity, and the y-axis is a number of samples. From the example below, we can see that in this example, most lyrics fall within the 0.4 to 0.7 range, meaning that the model captures partial semantic consistency but still have room for improvement. In summary, semantic similarity provides a more meaningful way to evaluate creative text generation like lyrics. It captures not only word-level similarity, but also emotion, theme, and meaning alignment between generated and original lyrics. Now, I'll hand it over to the next teammate who will present the results and performance analysis.
Alright, thanks for my previous groupmates presenting. My name is Wenhua Dong, and let's get into the results section. So on this slide, I'm showing two examples of generated lyrics from our model. The example on the left comes from the model trained with 1,000 samples. You can see that it actually produces something looks like a real verse. It apologizes, it talks about the emotion, it reacts to a situation. The lines flow, there's a little bit of rhythm, and it feels like a narrative. So this is the kind of structure that we are aiming for. Now compare that with the example on the right, which comes from the model trained on 500 samples. And here you can see one of the main failure modes, repetition. It basically gets stuck repeating the same line again and again. That's a sign that the model hasn't fully learned to move a sound forward. And it's also a decoding issue. We use the mostly greedy decoding, with only light repetition control. So the main message from this slide is, with more data, the model is able to write something that feels like lyrics. With structure and emotional arc, with less data, it's much more likely to move. And now let's look at the table. We evaluate lyric quality using a semantic similarity score. And here we show the example of two models. So generally, higher is better. And here we show the average, maximum, minimum, and maximum score. So there are two important takeaways here. So first, the ceiling gets higher as we add more data. With 1,000 training examples, the model can sometimes produce really strong lyrics. That's what we just saw on the previous slide. But second, the results become more inconsistent as the dataset grows. You can see the standard deviation increasing, so we can get more really good generations, but we also still get weak ones. In other words, more data gives us higher heights, but not perfectly stable quality. We also generate our results in different models, and we show them in our paper for deeper analysis. So now I will let my roommate move on to the discussion section.
Hi everyone, my name is Shiqi, and first I'd like to thank my teammates for the clear explanation of the experiment results. And now I will wrap up our presentation by talking about the main challenges we faced, the future directions, and the broader impacts of our project. So, as you just heard, each model behaved differently across datasets. And while the results were encouraging, we did encounter several challenges. So first, limited computation power and time made it hard for us to fully explore the best hyperparameter setting during the fine-tuning. And second, we had evaluation limitations. So first, we initially wanted to use the lyric birds, but due to the technical issues, we used the rock instead. However, this method mainly focuses on the word overlap, so it doesn't capture the lyric creativity or rhythm. And third, the models were quite sensitive to the prompt and the context, meaning small changes in phrases could lead to a very different lyrics. So from these challenges, we also see the three clear directions for improvement, like expanding the dataset to cover more diverse lyrical styles, optimizing the fine-tuning methods like LoRa or reinforcement learning, and improving the evaluation frameworks with human or semantic-based metrics. So to summarize, in this project, we fine-tuned 3 large language models on a Kaggle lyric dataset to generate lyrics from song titles. And the larger dataset produced more coherence and narrative lyrics, and the DeepSeek performed slightly better overall. And beyond these results, this project highlights how large language models can enhance the creativity and understand the rhythm and meaning, and even support cross-cultural lyric generation in the future. So that's all for our presentation, and thank you for listening and your attention.